Time series regression. Now, time series has many of the same mechanics as ordinary least squares regression, but there are some fundamental differences that have to do with the structure of the data. When you've got time series data, you have a sequence of information, and at any given time, changes across time are actually not that significant. If you look at the budget of a country or the GDP of a country or an income of a person, you're looking at smaller increments of changes. This has an effect in that it biases the results, and we need to compensate for it. One of the consequences is that we have hidden correlations in a given time period from previous time periods. If the relationship is to the immediately preceding time period, we call that first order serial autocorrelation. If it comes in 2 time periods or 3 time periods or 4 time periods, those would be other orders of serial autocorrelation. So in order to run ordinary least squares on time series data, we have to use a different method. And that's what we're going to cover here. The time series regression procedure. So it's a modified form of the linear regression. In the notes, I have all of the steps exhaustively laid out. Many of those steps overlap with the steps in linear regression, and so I've left all those notes in the time series ordinary least squares regression notes, but we're not going to go through all of those steps because it's very repetitive. Things like multicollinearity and checking for heteroscedasticity, all those you already know, and when you run your own time series, you would run them just like you would for a normal linear regression. Their ordinary least squares regression and time series regression are identical. So we're going to do a diagnosis of the first order autocorrelation by using something called a Durbin-Watson test. And if we have serial autocorrelation, then we're going to apply what's called an autoregression. An autoregression is an ordinary least squares algorithm which compensates for the serial autocorrelation. Now, the data set we're going to use can be found as SPSS China Save. It's going to have an N of 126. I'll open data. Here we go, SPSS China Save. This is an international relations data set. It's constructed using the correlates of war. It's got a large number of variables and 126 cases. And it's basically a comparison of China's power to the power of some other major powers across a number of variables like population, urban population, energy production, these sorts of things. So the model of interest is how does the relative power between China and its main competitors and the presence of big wars and the presence of nuclear weapons affect the level of interstate violence between China and its target state for a particular dispute between 1860 and 1985. So this is actually a time series, meaning each of the data points is sequential across time, and so we have gradual changes in the values as China gets stronger and other countries become relatively less strong. So the formal model is going to be rat-urb, which is the ratio of the urban populations, and nukes and the big war, as they predict the abbreviated hostility dependent variable. So the very quick variable definitions: rat-urb, the ratio of the urban population, is a concept of relative power. It's the sum of the US, Russian, and Japanese urban populations divided by China's population. Nukes is the presence of a nuclear umbrella either for or against China during a dispute, and it's thought to have some sort of pacific effect. It's a dummy variable, valued at 0 for the absence of an effect and 1 for the presence. Big war is the presence of a large-scale conflict that renders China a target of conflict or makes it incapable of staying outside of a conflict initiated by other great powers. It's a dummy variable valued at 0 for absence of the effect and 1 for the presence. So we're looking here at 2 dummy variables, nukes and big war. And the dependent variable, abbreviated hostility, is the level of interstate violence between China and the target state. And here we have a 21-point scale between 1 and 21, each indicating a higher level of hostility. So again, if you go to the notes, you'll see all of the procedures that you have to follow. So you don't have to go back to ordinary least squares. You can simply stay with the time series notes and follow through there. And the first step would be to check skewness and kurtosis, which we're not going to do. We're going to skip that. The second step is to check for multicollinearity. We're also not going to do that, but it's in the notes. And for both of those, we have normality and we have no multicollinearity. You would then do a scatter plot to assure linearity, and that's also doable. There is an example in the time series notes of a curvilinear relationship and how to approach solving that problem that involves variables from this model. It looks at population ratios. And we're going to skip that as well. We're going to skip excluding outliers. And we're going to go right to running the linear regression itself. So you know how to do this. We go to Analyze. We go to Regression and Linear. The dependent variable is abbrev host. It's down here. There's a lot of variables here, so it'll take us a while to find it. Let's open it up so we can see all of the different variables. So we're looking for nukes and big war. So we have down here, we have big war is here. We have nukes here. These are our 2 dummy variables. We're now looking for rat-urb, which is the ratio of the urban populations. And this is wide enough, so we should be able to find it. Yeah, it's probably up here. So rat, US, rat, mill, rat-urb is right up here. So we insert rat-urb. Again, we're going to save the predicted values. We're going to save the standardized values. For the residuals, we're going to save the studentized. And we click continue. No, and here, yeah, here we click continue, and we're going to go now to statistics at the top, and we're going to click on Durbin-Watson. Now and we also have case-wise diagnostics. You can click on this if you want to look for outliers that are 3 standard deviations or beyond. We're not going to click on it. It's a useful thing to know. So the Durbin-Watson is crucial. This is going to tell us how severe our serial autocorrelation is. Okay, and whether or not we need to run an autoregression in order to solve the problem, and then it'll tell us how well the autoregression did in solving our problem. So now we go to plots, and in plots we're going to put the standardized predicted into X, so that's Zulu pred into Y rather, and we're going to put SD resid, the studentized residuals, into the X, and we're going to click continue, and we have our model here, and we're going to click OK. And very quickly we can see the adjusted R squared is 0.399, which is good. We can see there's good F significance. We can see that all 3 of the independent variables are significant. All right, so things look good. It looks like we have a very strong model here. However, we go here to the model summary and we see a Durbin-Watson of 1.448. And I can tell you right away this is a bad value. A good value, as a rule of thumb, is a 2. If you have a 2, you can be certain that your serial autocorrelation problem is either non-existent or has been taken care of by autoregression. In this case, we have a problem. We're using ordinary least squares. It's not compensating for serial autocorrelation, and so we have a bad Durbin-Watson. So what we're going to do is we're going to run an autoregression, and this can only be done through the syntax. And once we've run the autoregression, we're going to go back and we're going to look at how we calculate the Durbin-Watson. Okay? But first, let's take this regression and rerun it. Okay, so we're going to go up here to Analyze, Regression, Linear, and we're going to click Paste. And voila, we have our syntax window. Now what we need to get is the autoregression syntax, which I have conveniently put on this PowerPoint slide. So the technique we're specifically using is Cochrane-Orcott autoregression, which is coded as CO. Okay, so this is actually what we just ran now. I'm going to have to go find the code for Cochrane-Orcott, which is here. Cochrane. Voila, here it is. So we're going to take this code, and we have to make sure, of course, it's tailored for the particular model that we're running. So the important thing is that we have a period at the end and that we've inserted the correct variable. So here we have a brief host. We've got nukes, big war, and rat herb. So we're going to run this autoregression, and you can see the code areg, and method CO refers to Cochrane-Orcott. So boom, we've rerun this. So here we have two types of models that are being run. First, the autoregression is going to run the original ordinary least squares autoregression and show us the result. And we can see here with the Durbin-Watson of 1.448, we have a problem. The values are, well, they're suboptimal. Clearly there's serial autoregression happening. So we go down to the final iteration, and the final iteration shows that we now have a Durbin-Watson of 1.898. And what this is going to do for us is it's going to give us more accurate coefficients. Okay, and so we look here now, and we've got the unstandardized B coefficients divided by the standard errors, giving us t values, and those values are still significant. And we have an adjusted R squared of 0.281, which is a more accurate, deflated estimate of the amount of variance explained in the dependent variable by the independent variables. So the Durbin-Watson here is calculated for us automatically. But let's take a look at how we would read the table. So this is the standard table for the Durbin-Watson statistic. And you can see this chart down here below. And the way to interpret this chart is, in this zone here on the left, if we have a value in this zone, it indicates that we definitely have serial autocorrelation. If we have, and that's between 0 and D underscore L. If we have a value in D underscore U that carries all the way up here to the extreme right, then we don't have serial autocorrelation, or the serial autocorrelation has been corrected. If we have a value between underscore DL and D underscore U, then the test is inconclusive. Regardless, if it's inconclusive, or if you have serial autocorrelation, or if you have time series period, you should always run an autoregression, and you should always test it with a Durbin-Watson. even if you're not going to get serial autocorrelation, because generally you will get serial autocorrelation. All right, so as usual, the null hypothesis is of no positive serial correlation, and we obviously want to be able to reject that estimate. So let's take a look at the table here and look at what values we have to select. So here we're here at the 5% one-sided level of significance. Now for Durbin-Watson, the one-sided level of significance, it normally implies you have a sense of the direction of the hypothesis, but it's also a more conservative estimate for the Durbin-Watson, and so we're going to take the 5%. That's what we've chosen in this particular table. Now, we're going to choose K prime is equal to 3, because that's the number of independent variables that we have. We have 3 independent variables, and so this is going to give us our values of D underscore L and D underscore U. And we're going to go down these two columns right to the bottom. N is 100. We actually have 126 cases, which exceeds 100, so we're going to select 100 and match it up with the column. And so we have an intersection here of 1.61 and 1.74. So 1.61 here at DL and 1.74 here at D underscore U. So before we had autoregression, we scored about a 1.4 on the Durbin-Watson, which is clearly in the area for the presence of serial autocorrelation. And after we ran the Durbin-Watson, we had a 1.84, which is higher than D underscore U at 1.74. So running the Cochrane-Orcutt autoregression solved the problem of serial autocorrelation. So we can now have confidence in the values that we selected. And you would continue running the post-diagnostics that you would normally for a regression. You would plot to detect if there is heteroscedasticity, and then you would proceed to this step, which is examining the first order serial correlation. And it should be pointed out that the Durbin-Watson does not test for second, third, or fourth serial autocorrelation, but there are very sophisticated techniques, ARIMA, which are autoregressive integrated moving average techniques, which are used to make much more sophisticated estimates than a time series, but they also have a great many more moving parts, and so they're a lot more complex, and in that sense they're not used very often. And they're more used for prediction than validation. So the significance tests are not quite as clear in ARIMA as they would be in time series. So let's go on to the last step, just because it's interesting, and that is the regression equation, the prediction equation. So here we've taken the constant, which is the y-intercept. We've added the coefficients for the 3 independent variables, big war, rat herb, and nukes. Equals the 21-step abbreviated hostility dependent variable. So I've assumed here we have World War III going on between the USSR and China, so I put a 1. I assume that there's a nuclear umbrella present from either country. I assume that China's urban population is about half of its opponents, so the value is around 2. I plugged it in, those values into the coefficients, and it gives us a 24.875, which is on a 21-point scale. It's very high likelihood that China would be in a high violent dispute with a neighbor. In fact, it's 21 plus. So we've successfully made a prediction using time series using this model.